So welcome to the last lecture of this mini course on packing and covering. The subject is the Mengerian property. So let's recall the key definition here. A 0,1 matrix M is Mengerian if the system Mx greater than or equal to 1, x non-negative, is TDI. And as we saw in the first lecture, this is equivalent to having the primal dual min-max relationship, where the minimization problem is the set covering problem and the maximization problem is its integer dual, and we want this to hold for every non-negative integer objective function of the set covering problem. In addition, for every 0,1 matrix, we have an associated clutter, and we're going to say that that clutter is Mengerian if the corresponding matrix is Mengerian. So let's look at some examples of Mengerian matrices, or equivalently clutters. And the first one arises from odd cycles in graphs. So let F be a clutter of odd cycle of some sine graph G sigma. Then F is not Mengerian if and only if F has a Q6 minor, where Q6 is the matrix we've seen a number of times now. So one direction is easy, namely if you have a Q6 minor, then you're not Mengerian. So you need two elements for that argument. One is to show that the Mengerian property is closed under taking minors. We didn't prove that, but it's easy to show. And the second one to just remember that Q6 is not Mengerian, and we've seen that in the first lecture. Now, there's an equivalent way of characterizing the Mengerian property in this case, and that is to just look at the sine graph. So F is not Mengerian if and only if the sine graph contains as a minor odd K4, where odd K4 is just a graph K4 where every edge is odd. So why is this equivalent? Well, we've seen that taking minors in a clutter is equivalent to taking minors in a sine graph, so that proves the equivalence between 2 and 3. Another very important class of Mengerian clutters arises from directed graphs. Right? So a graph is directed if you just add direction to the edge of a non-directed graph. So the first notion we'll need is that of a die cut. This is short for directed cut. And what is a die cut? Well, you take a cut in the underlying graph where all the edges are directed from one shore to the other shore. So here's a little example, right? We're looking at the cut where we look at all the edges going between U and U bar, right? And all the edges are going in the same way. The second notion is a notion of a die join. So a die join is a set of edges in a directed graph such that after contraction, if you contract all of those edges, the graph becomes strongly connected, which means that there's a directed path between every pair of vertices. So let's look at an example. Consider the two red edges there. If I happen to contract those two red edges, you get the graph on the right, and this graph is easily seen to be strongly connected. Now, clearly, every directed cut has to intersect a die join, because if you have a directed cut, your graph is not strongly connected. In fact, you have the stronger relationship between die cut and die joints, namely die cut and die joints are blocker of one another. So here's a classical result of Lucchesi-Younger, and it says that the clutter of die cuts is Mengerian. So I would like to restate this result just in a language of directed graphs, and it'll be easier to have a definition first. So let's say that a clutter packs if for the associated matrix I have the following min-max relationship between the set covering problem and its integer dual, where we're looking at the objective function of all ones. So clearly, if you Mengerian, then you pack, because being Mengerian means that you have the min-max relationship that holds for all non-negative integer weights, and so in particular it will hold for the integer weight vector of all ones. So the clutter of die cuts has to pack, and what does that say in the language of directed graphs? Well, the optimal solution to the minimization problem there is going to be a set of edges that intersect every directed cut. So it's going to be a die joint. So the minimization problem is looking for a minimum size die joint. And the maximization problem has one variable for every directed cut. So you're looking for a maximum number of pairwise disjoint die cuts. So here's a little example. We have in orange 2 disjoint die cuts, and your 2 red edges or a die joint of size 2. Alright, so I stated the result again. The clutter of die cuts is Mengerian, and you could say, well, what if I replace die cut by die joints? Is it true that the clutter of die joints is Mengerian? And this was a conjecture of Edmonds and Giles. And it turns out that this is not true, and here's the example which is due by Scriver. So in this example, you're going to need 2 types of weights. You have weights 0, which are indicated in green, and weights 1, which are indicated in dark blue. So I want to sort of sketch out why is it that this example shows you that the clutter of die joints is not Mengerian. So let's look at the minimization problem there, right? So we do minimizing for the weight W, and the matrix M that we're considering is the one that arises from die joints. So this minimization problem is going to look for a set of edges that intersect every die joint, so it's going to look for a minimum weight directed cut. So we have a directed cut of weight 2, namely the one which is indicated in pink, and in fact there's no directed cut of size 1, so the optimum value for that minimization problem is 2. So now let's look at the maximization problem there. So here we have one variable for every die joint, and so what we're looking for is the largest size of a collection of die joints that are pairwise disjoint and that are contained in weights with weight 1, so in the blue weight. So I'd like to claim that the optimal value to this maximization problem is 1, which will prove that the clutter is not Mengerian, the clutter of die joints. So suppose for a contradiction that it's 2, so it means that I can find 2 die joints, say red and orange, that are pairwise disjoint and that are contained in the blue edges there. Now it turns out that this is pretty constrained because look at every one of the pink vertices. The edges which are incident to each of those pink vertices form a directed cut, which means that I must have one edge which is contained in a red die joint, incident to each pink vertex, and one edge which is contained in the orange die joint, which is incident to that pink vertex. So you don't have too many ways of picking those red and orange die joint if they exist. In fact, you have 4 distinct ways of doing it. So let me just pick one way and see what happens. The other cases are similar. Now, is orange and red 2 different die joints? And the answer is no. You have that directed cut, which is disjoint from the red edges. So the red edges don't form a die joint. Okay, so Edmonds and Giles holds for a very interesting special case, namely that if you have the property that every source is connected to every sink, so there's a directed path from every source to every sink, then in fact the clutter of die joint is Mengerian. It's a very nice result, and you might wonder if you can do better. In fact, you have the following conjecture. The conjecture is that all you need is to have one source that has directed paths to all the sinks, and to have one sink that has directed paths from all the sources. Right? So this is a much weaker condition, and this problem is wide open. Another interesting conjecture that arises from the Lucchese-Younger is the following. So let's just write down again what it means for the clutter of die cuts to pack. It says that the minimum size of a die joint is equal to the maximum number of pairwise disjoint die cuts. So what happens if you just interchange the role of die joints and die cuts in that expression? And Woodall has conjectured that, in fact, the equality should still hold, so that the minimum size of a die cut should be equal to the maximum number of pairwise disjoint die joints. So this seems to be a very attractive conjecture, because this is a conjecture about all directed graphs. That makes it very attractive. It also seems to be very hard. And one of the reasons this is hard is because the corresponding weighted version of that conjecture, which would say that the clutter of die joints has a Mengerian property, is not true, as we've seen. So the next topic is going to be the replication operation and the packing property. So let's go back to perfect graphs, and let's consider graph G, and let's suppose that M is the stable set matrix of G. So this is a matrix where the rows are the characteristic vectors of the stable sets of G. And let's just remind ourselves of the definition of a perfect graph. So the condition is that for every induced subgraph H of G, omega of H is chi of H. So the size of the largest clique is equal to the minimum number of colors needed to color H. So we can restate this definition about perfect graph just in terms of matrices. So I claim that the restatement is as follows. So for every column submatrices n of M, we have this max-min relationship, where the maximization is really the set packing problem for that submatrix n, and the minimization is its integral dual. So why are we looking at column submatrices? Because looking at column submatrices of the stable set matrix is equivalent to looking at induced subgraph, and the maximization is computing the size of the largest clique, and the minimization is computing the minimum number of colors needed to color the corresponding induced subgraph. Okay, so what I'd like to do is to find an analog of that definition for set covering. Right, so this is our definition there. So what does it mean to look at column submatrices? Well, it essentially, we're looking at a containment operation that preserves perfection. So we would translate that column submatrix operation into minors, and then the max-min relationship that corresponds to doing the largest value I get from the stable set, and that should be equal to the integer dual problem there. Then we replace this by the minimum value of the set covering problem, that is equal to the optimal value of the integer dual. So what we get is simply this. A clutter F has the packing property if for every minor H of F, H packs. So H pack is our min-max relationship, which is the analog of the max-min relationship above, and the minor operation corresponds to the column submatrix. Right? So this notion of packing property is the exact analog of perfect graphs, but for set covering problem. Right? So again, let's look at this definition. We're requiring that for every minor, the minor packs, right? So when we say a minor, we're not requiring that it's a proper minor. So in particular, the clutter itself should pack. All right, so now that we have an analog to the definition of perfect graph buffer set covering, we can go back and think of some of the results we had about perfect graph and see whether those results extend to that analogous property for the set covering problem. So one thing that we proved was that if you have a perfect graph and you have the matrix M, which is a stable matrix of that graph G, then the associated system there is going to be TDI. So perfect graph, the analog now for set covering, is packing property, and the analog to the system Mx smaller than or equal to 1, x non-negative being TDI, is the Mengerian property. So we have the following conjecture, that if F has a packing property, then F should be Mengerian. In fact, it's easy to see, and you should do it as a little exercise, that the Mengerian property implies the packing property. So really the heart of the conjecture is showing that the packing property implies the Mengerian property. So this is known as the replication conjecture. And you may ask, why is it that we're calling this the replication? And it is because there's a different version of that conjecture which is equivalent. And I would like to restate that different version. So we have a replication operation. So you start with a clutter F, which has some element in the ground set. Let me call it E. And now we're going to create a new clutter, say H, by replicating that element E. And by that we mean that we're first adding some element in the ground set. That new element is going to be E bar. And our clutter H is going to contain all the elements that didn't contain E, that were in F. And for every element that contained E, that is in F, I'm going to keep that element and then remove E and add the new element E bar. So it might be easier to visualize what we're doing there to just look at the corresponding matrices. So on the left, I have the matrix which correspond to the original clutter F, where the first column is the element E. And on the right, I have the matrix which correspond to the clutter after replication. So now I have two columns, which are replacing that column E. I have E and E bar. And if you look at that matrix there, you can see that we're doing exactly on the matrix what we've done on the clutter. Now, there's a nice connection to duplication if you do that. Namely, if you start with a graph and you look at its stable set matrix, and then you do the duplication that we've seen in the second lecture, and you look at the stable matrix of the duplicated graph, what you will see that the relationship between the first matrix of the original graph and the duplicated graph is exactly that replication operation. So duplication and replication, when you look at it from the matrix point of view, are exactly the same operation. So now here is the different version of the replication conjecture which I promised, and it just says that if you have a clutter that has a packing property, then so does any replication. So the packing property should be closed under replication. And it's not very hard to show that this conjecture is in fact equivalent to the original replication conjecture, right, which says that the packing property and the Mengerian property are equivalent to one another. And to see how you go from one conjecture to the other, it's very much like the argument that we used when we showed that if you have a perfect graph, then you can construct a TDI system using the duplication lemma. So I'll leave that as an exercise. So the replication conjecture predicts that the packing property implies the Mengerian property. Now we proved in the very first lecture that the Mengerian property implies idealness. So you expect that the packing property should imply idealness, and this is indeed the case. So here's a proposition. If a clutter has a packing property, then it must be ideal. And this is a nice application of Lehmann's theorem, another nice application of Lehmann's theorem. So what we're going to do is to prove the counterpositive. So we'll prove that if a clutter is not ideal, then it doesn't have the packing property. Right? So suppose F is not ideal. Then F has to contain a minimally non-ideal minor H. And we will show that H doesn't pack, right? Which will prove that F didn't have the packing property as required. So one possible outcome for a minimally non-ideal clutter is that the clutter is a delta. And then you can just check that it doesn't pack. So we'll assume that H is not a delta, and then we can use Lehmann's theorem. So Lehmann's theorem is going to tell us that we have a unique fractional extreme point x bar of the set covering polyhedron. And again, we can look at all the left-hand side of the tight constraint for that extreme point and collect all of those to make a matrix A. We can look at all the neighbors on the set covering polyhedron of x bar and make a matrix B. And then we have this very nice matrix equation, A transpose B is J plus Di for D greater than or equal to 1. Now, by a result of Bridges and Reiser, we have that the matrix equation above, this A transpose B is J plus Di, implies that A is R regular and B is S regular. So what do we mean by R regular? We mean that A has for every row R1s and for every column R1s as well. So now let's take that matrix equation and we multiply on the left by the row vector of all ones, and we multiply on the right by the column vector of all ones. And using the fact that A is R regular and B is S regular, we get the following expression for the left term and the right term. And that allows us to express the number of column n as being equal to Rs minus D. Now observe that x bar is an optimal solution to this minimization problem. So this is the LP relaxation of the set covering problem for our MNI minor H. And what value do we get for x bar? Well, it's 1 transpose x bar. X bar is the vector with 1 over r for every one of the components. And so we get the value n over r, and we know what n is. It's Rs minus D. So we can simplify, and we get the value S minus D divided by R. Now it's easy to check that D has to be smaller than R. You can just get that by looking at the matrix equation. But then that tells us that 1 transpose x bar is not in Z. And so it tells you in particular that H doesn't pack. And that's what we wanted to prove. So next, we're going to look at excluded minors for the packing property. So one question you may have is, why are we looking for excluded minors for the packing property and not for the Mengerian property? And the short answer is that these two properties are supposed to be the same if the replication conjecture holds. So what's the definition we're looking for? Well, a clutter F is minimally non-packing if it does not pack, but every proper minor of F pack, right? So minimally non-packing clutter are somehow the smallest clutters that don't pack. And one thing we proved just a second ago is that clutters with the packing property are ideal. And that implies immediately that a minimally non-packing clutter must be either MNI, so minimally non-ideal, or ideal, right? Because if you have a proper minor that is non-ideal, then you also have a proper minor that doesn't pack. All right, so there's going to be really two classes to look at: minimally non-packing clutter that are MNI or that are ideal. So let's look at the first class. And for that class, it's going to be helpful to write down the relevant part of Lehmann's theorem. So we have this matrix equation A transpose B equal to J plus DI that we've seen a number of times now. And we're going to introduce a definition. We're going to say that in an MNI clutter is thin if D is equal to 1. So an example of a thin MNI clutter, for instance, are the odd holes, or the blocker of odd holes. So why is this relevant? Well, because we have this following result. So if you have a clutter F that is an MNI clutter, and you tell me that it's also minimally non-packing, then it has to be thin. And in fact, the question of whether the converse holds is open, and it would be very nice if the converse holds, because it would tell you that you have a way of distinguishing between MNI clutters that are minimally non-packing and not minimally non-packing. Namely, the only thing you have to do is check whether they're thin or not. Right? And since it's unlikely that we can describe all the MNI clutters, this is sort of a partial characterization of which ones are going to be minimally non-packing and which ones are not. So now we're going to look at minimally non-packing clutter that are ideal, and I want to discuss what seems like a far-fetched conjecture, but it's been around for a long time, and I think it's quite possible that it's actually true. So what does the conjecture say? It says that if you take a minimally non-packing clutter that is ideal, then you must have a cover of size 2. So let's look at an example. Here we have Q6. We've seen that this doesn't pack. In fact, it is minimally non-packing. And we've also seen that it's ideal. And it has a cover of size 2. In fact, it has multiple. One example would be 1 and 6. So what is the motivation for that conjecture? In fact, this is where it came from. It's the fact that the tau equal to 2 conjecture imply the replication conjecture. And I'm going to show you why this is the case. So we're going to look at the version of the replication conjecture that says that replication preserves the packing property. And we're going to proceed by contradiction. So imagine that you have a clutter that has the packing property, but after replication, it stops having the packing property. So that clutter must contain a minimally non-packing clutter, and it better contain the replicated element, because otherwise the original clutter didn't have the packing property. Right? So if you have a counterexample, then you must have a minimally non-packing clutter F with a replicated element, say E, and its replication E bar. So now, because you have the tau equal to 2 conjecture, it would tell you that you have a cover of size 2. So in particular, you cannot have disjoint sets in that clutter, because otherwise it would pack. On the other hand, I tell you that this clutter packs. So if I take a contraction of that, the covering number is going to be at least 2. So after contracting E, I must have 2 disjoint sets. So that tells me that I must have had 2 sets, say S1 and S2, that intersect exactly in the element E. But now what you can do, and here you're using the structure of the fact that you have a replicated element, what you can do is take, say, the set S1, remove E, and add the replicated element E bar. And now you take that set and you notice that it's disjoint from S2. So now you have two disjoint sets, but then that tells you that in fact it packs, and that's your contradiction. So the last thing I'd like to point out is that the tau equal to 2 conjecture holds for binary clutters. In fact, you have the stronger result that says that a clutter is Mengerian if and only if it doesn't have Q6 as a minor. Note that this theorem immediately tells you that the Mengerian property and the packing property are the same, right? Because if you have the Mengerian property, you certainly have the packing property. And if you don't have the Mengerian property, then you must have a Q6 minor, but QC doesn't pack. So you also don't have the packing property. And finally, because the tau equal to 2 conjecture holds for binary clutter, the replication conjecture also holds for binary clutter. And this marks the end of this lecture and the end of this mini course on packing and covering. I'd like to thank you for your attention. I very much regret not being able to see you in person. I hope everybody keeps safe, and I'd like to thank Ahmad Abdi for many exciting discussion on the subject of packing and covering.